Okay, so here's the third problem about related rates. So let's read the question. So we're told that there is a light at the top of a 5-meter pole. A child 1.5 meter tall walks towards the pole at 2 meters per second. And we were asking, so we're told that the child walks at a constant speed of 2 meters per second. And we're asking, what is the velocity of the tip of the child's shadow when she, the child, is 6 meters from the pole? So imagine this, you have a light at the top of a pole, a child is walking towards it, so of course the light is shining on the child, which will create a shadow on the ground. And we are asking for the velocity of the child's shadow, the tip of the shadow, when the child is 6 meters from the pole. So as always, first let's draw a picture of the situation. We have the ground. We have our pole, which is 5 meter high. And the light is at the top of this 5 meter pole. So this is the light. And this is not changing, it's a constant. It's always equal to 5 meters. Now we have a child walking towards the pole. So imagine the child is standing here and the light will shine on the child and create a shadow. So imagine that this is the child right here. That's the child's head. And you can see that the light will be shining on the child, and this will be the shadow of the child, right? The light is shining on the child, and here you get the shadow, and we want the velocity of the tip of the child's shadow. Well, imagine that this is the shadow. Well, this is the light, but this is the shadow, and so this will be the tip of the shadow, the end of the head of the shadow. So we want the velocity of this tip when the child is 6 meters from the pole. Well, let's look at our variables. The child is always 1.5 meter tall. So this is also a constant, 1.5 meter. Now the distance between the pole and the child is changing, right? Because the child is walking towards the pole. Therefore, the length of this segment is a variable. Let's call this, say, x. Now let's look at what we know, and then we'll see that there's also a variable here that we are interested in. Let's first write down what we know. As far as rates of change are concerned, the child is walking towards the pole at 2 meters per second. That's the speed at which the child is walking. That's how fast this segment is changing, right? So that's dx over dt. And this is the at all time t because we're being told that the child is walking at a constant speed, velocity of 2 meters per second. But if you write this, this is actually wrong. Think of it. What happens to x over time? X is a function of time, but as time goes by, the child is walking towards the pole. Therefore, as time goes by, x is getting smaller and smaller and smaller. The distance between the child and the pole is shrinking. Because x is decreasing as a function of time, it has a negative derivative, a negative rate of change. So you really have to be careful about this. When variables are increasing as functions of time, they have a positive rate of change, but when variables are decreasing as functions of time, they have a negative rate of change. What do we want? This is the only rate of change that we're given. What do we want to find? We want the velocity of the tip of the child's shadow. That's the velocity of this, because of course as the child is moving, the tip of the shadow will be moving as well. And we want the velocity of the tip of the shadow. Here's where you have to be really careful. If you take this line segment and ask for the derivative of this line segment, the length of this segment as a function of time, this would actually be wrong. When you want the velocity of an object, you have to have as a point of reference a fixed point, a point that is not moving. But if you take this point right here as your reference point for the tip of the shadow, this is wrong because this is not a constant point. As time goes on, this will be moving. So your reference point must be the position of the pole. So we have a new line segment connecting the point of the pole with the tip of the shadow. This is a variable, call it y. And now, the rate of change of y as a function of time will give you the velocity of the tip of the child's shadow because the reference point, being the pole, is constant. And now we have what we want. So dy over dt. But be careful, we want the velocity of the tip of the child's shadow specifically when the child is 6 meters from the pole. Therefore, when x is equal to 6. And now that's what we want to find. Well, if you look at the picture, you may ask, well, what is the length of this segment? This will also be changing. So it's also a variable, but there is no need here to use a third variable, say z, because think of it. Y is the length of the long line segment. If the short segment here has length x, this must be y minus x. And now we have our picture. We know this rate of change, we want this rate of change, and of course, if we want this rate of change knowing this one, we have to relate y with x. So now we're looking for, as always, our relation. Well, let's see what we have here. There's no need to introduce angles because nowhere in here are we mentioning angles. We don't know anything about them. Let's not introduce them. But look at the geometry of the picture. There are here two triangles. There's a small triangle, then there is the larger triangle. And both are right triangles. And if you look, there are also similar triangles. They have the same angle of 90 degrees here, pi over 2. They share the same angle at the base. Therefore, this angle here is also the same as this angle here. So we have two similar triangles, the large triangle and the small one. And when we have similar triangles, what is constant is the ratio of common sides. So if we take the height of the bigger triangle, dividing this by the height of the smaller triangle, 1.5, this ratio will be the same as the ratio of the length of the bigger triangle, which is y, over the length, the base, right? This is y is the base of the larger triangle, over the base of the shorter triangle, which is y minus x. And now we have a relation. We have related y with x, right? Because for similar triangles, the ratio of common sides will be the same. So the height of the larger triangle over the height of the smaller triangle will be the same ratio as the length of the base of the bigger triangle over the length of the base of the smaller triangle. Now again, x is a function of t, y is a function of t. So both the left and the right hand side are functions of t. So we could here be naive and differentiate both sides with respect to t and use the quotient rule here. But let's be clever about this. If we're not happy with the relation we have, we can try to rearrange it to hopefully make our differentiation a little simpler. Well, let's clean this up a little bit. The left-hand side, 5 divided by, well, 1.5, that's just 3 over 2. If you divide by 3 over 2, same as multiplying by the inverse, 2 over 3. So what you get is 10 over 3. That's equal to y over y minus x. To avoid the quotient here, just multiply across by y minus x and by 3. So this will be equivalent to 10 y minus x being equal to 3y. We wanted the rate of change of y, so let's isolate here y as a function of x. So let's multiply this out, and we'll get 10y minus 10x equals to 3y. Send the 3y on the left, the negative 10x on the right, you'll get 10y minus 3y is 7y, which will be equal to positive 10x. Finally, y will simply be equal to 10 over 7x. And now we have a much simpler relation, right? This was the original relation, looking at the ratio of corresponding sides of similar triangles to this relation, and now you see we can differentiate and avoid the quotient rule altogether. So don't be too hasty when you have your relation to differentiate. Ask yourself, could I rearrange it to make my life simpler? And the answer is here, well, yes, this will be much simpler. Now we're good to go. X is a function of t, y is a function of t, because as t changes, both x and y are changing. So both the left and the right-hand side are functions of t. Therefore, they have the same derivative. So let's differentiate both sides with respect to t. The derivative of the left-hand side with respect to t equals the derivative of the right-hand side with respect to t. Well, this is just the derivative of y with respect to t, so it's dy over dt equals 10 over 7 here is a constant multiple, so it will just stay there, times the derivative of x dx with respect to t, and that's just dx over dt. Finally, we wanted the derivative of y with respect to t when x was equal to 6. And keep in mind that dx over dt was always equal to negative 2. So we can now evaluate. And if you look, the derivative of y with respect to t does not depend on x. So this could have been x equals 6, x equals 3, x equals 1. dy over dx will never depend on x. You see, dy over dt, dy over dt does not depend on x. So the derivative, dy over dt, at x equals 6 is, well, 10 over 7 times dx over dt, and that's always negative 2. So you see the x equals 6 does not factor in. This would have been the same answer if x was 5, 4, 3, 2, 1. And finally, we get negative 20 over 7. So if you approximate this, you'll get approximately a rate of change of negative 2.86. And now we can include the units. The length, right? Y was the length of a segment. Length is given in meters, time in seconds. So in the end, we have meters per second. And what's interesting again here is that we have a negative rate of change for y. Well, this was expected because as time goes by, the child is getting closer to the pole. Therefore, the tip of the shadow will also move in this direction. Therefore, y will be decreasing, and if a variable is decreasing, it has a negative rate of change. And you can see that the rate of change of the tip of the shadow is also constant, right? It's always, no matter what value of x is, it's always roughly negative 2.86 meters per second. And what's kind of neat is the shadow is moving faster than the child. The child is moving at a speed of 2 meters per second. So this point is moving at a constant speed of 2 meters per second. But this point, the tip of the shadow, is moving also at constant speed, but not of 2 meters per second, but approximately 2.86 meters per second. So the tip of the shadow is moving faster than the actual child.